Hello everyone, my name is Eric Persine and I'm happy to introduce you to IR cycling hand signal detection. As for the motivation behind this project, cycling is dangerous. According to the CDC, 130,000 cyclists are injured in crashes on the road each year, and 1,000 more are killed. Here in Fort Collins, we're lucky enough to have dedicated bike lanes everywhere, but that's not usually the case. One way cyclists keep themselves safe is by using hand signals to convey their intentions. However, especially in low light conditions, hand signals can be difficult to see. Also, a lot of pedestrians just aren't so familiar with their meanings. So the goal of this project is to increase visibility and awareness of cycling hand signals using machine learning and a Raspberry Pi-based embedded system that'll be mounted on the back of the user's bicycle. Regarding related works, there are some pretty similar projects online, like this backpack and glove combination you see here. This project also uses machine learning to make cycling signals more visible. However, it relies on gyroscopic data from the glove and also requires additional gestures to the hand signals to make sure that they're recognized, like a left wrist rotation turn left, for example. I wanted my solution to not require wearing any extra device nor performing any extra gestures. So I decided on using video classification, but this project needs to work in both the day and the night, so this would require something like IR vision. The field of video classification has a lot of prior work to build on. There's pose estimation, gesture recognition, and a lot more. But there's surprisingly little work in IR video classification, at least of the scope I'm looking for this project. Because of this, and the fact that I'm using a fixed camera angle with relatively few classes of gestures, I decided to design my own model and dataset. And that brings us to the technical challenges. First of which is IR vision. I chose a camera that automatically switches between daylight mode and IR light depending on the light level. This is particularly useful when the light level around you changes rapidly, like if you're entering a tunnel. But it also means the same model needs to be capable of classifying images in both daylight and IR light. To accomplish this, I need to make my own dataset. Not only does it need variation in light level, but it also needs variation in clothing. It'd be really disappointing if I had to wear the same jacket every time and get it to work. Lastly, I need this to be a comprehensive embedded system that fits on the back of your bicycle. It needs to have a camera, video output, audio output, and a power source. So, the first thing I did was acquire my hardware and design a mount so I could start taking pictures. Here's the thing I came up with. Next, I got on my bike and took some videos. I cropped the output of the camera to the area you see here and downscaled it to 200 by 200 pixels. This is the standard for my dataset and also the input to my neural network. Now it was time to take a lot of pictures. I ended up with 27,000 images of the 6 classes you see here. About 50% of these images were taken in daylight and 43% in IR light. I also wore 23 different outfits, including gloves and different jackets. There's a 90-10 split between the test and validation sets, with no overlapping clothing between the two. And once that was done, I could finally get started on the model. For the model, I went with a single frame CNN for video classification. This treats every frame of video as a unique image. We miss out on the time dimension that way, but cycling hand signals are pretty static as far as gestures go, so that's no big deal. Using the model structure on the right, I trained a network on my dataset with 99.31% accuracy. I found that the hyperparameters that most affected accuracy were batch size, epochs, learning rate, and dropout rate. This is probably because the images in the dataset are randomly shuffled, regardless of gesture, time of day, and clothing. And it's a little difficult to see here, but this is a saliency map of all the important gestures. The final system ran at about 0.5 frames per second with exceptional accuracy. Here's a quick GIF of the project in action, but feel free to check out the demo if you can. Lastly, broader impact. This project was successful in increasing the visibility and awareness of hand signals. I think it serves really well as a proof of concept, but for practical use it does need a few key improvements. First of all, the dataset consists of one cyclist on one bicycle from the exact same angle and position. If you want to try it on your bike, you may need to make your own dataset. So to fix this, I would work on a more diverse dataset. Secondly, 0.5 frames per second is acceptable, but the system could definitely run a lot faster if you use smaller images. A 200 by 200 resolution isn't necessary. In retrospect, I would have tried 50 by 50. But overall, I am really proud of my work this semester and very happy to share it with you. Thank you for listening.